So hi everyone. I would like to introduce you to our next speaker, Ron Bonica. Ron is a distinguished engineer at Juniper, and he's here to talk to us about fast reroute on IP networks. Ron, all yours.
Well, thank you. Good evening, good night, good morning, good afternoon, whatever time zone you're in. And today we're going to talk a little bit about IP fast reroute. Now, IP fast reroute has evolved through three stages. At first, there was link-free alternates, LFA. Then remote link-free alternates, RLFA. And finally, topology-independent loop-free alternates, TILFA. We're going to step through each of them. But first, let's talk a little bit about what the problem is. Let's say for a minute you have a link failure in your network. Well, for some small period of time, you're going to be dropping packets while the IGP churns. The nodes on either side of the link failure are going to have to advertise the link failure. That information propagates through your IGP domain. Everybody recomputes their best path to everywhere else, and then things go back to normal. Now, this is called the convergence period, and connectivity isn't restored until the IGP converges. Now, how long does that take? Well, it depends on the size of your network, the size of your IGP domains, the speed that your processors are running at. If you're lucky, it might be milliseconds and nobody will care. If you're less likely, seconds, and maybe users will start to notice that if they're gaming or if they're doing IP telephony. And if it's really bad, it might be tens of seconds, and users will definitely notice that. So we have this idea of IP fast reroute. IP fast reroute protects some resource, either a link or a node, and it computes a repair path around that protected resource. When the protected resource fails, the node just upstream of the failed resource shifts traffic to the repair path so that connectivity is preserved during the IGP convergence period. Anyhow, that may have sounded like so much gobbledygook, so I'll give you a concrete example. Let's say for a minute, R2 calculates its least cost route to R7. That's going to go through R2, R5. Now, if R2, R5 breaks, R2 is going to black hole traffic destined for R7. And this black holing may persist for a while. Certainly, R2 has to install new routes to R7, but maybe other nodes also have to do that before the IGP reconverges. So for some small period of time, we're going to have black holing, and that's going to be called the convergence period. Now, we need two other words in our vocabulary. One is pre-convergent state. R2 is in a pre-convergent state regarding R7 from the time R2, R5 breaks until it installs a new route to R7. So what's the pre-convergence time? It's the time between the break till the time R2 gets a new route to R7. Then there's a post-convergence state. Once that new route is installed, R2 enters a post-convergence state. Now, there are three fast reroute solutions. They've evolved over time: LFA, RLFA, and TILFA. There are some things that all three solutions have in common, and there are some things that make all three solutions different. What they have in common is each of them has something called a point of local repair. The point of local repair is just upstream of the protected resource. It notices that the protected resource is broken first. The other thing they all have in common is something called a repair node. The point of local repair, the PLR, wants to get traffic to the repair node during the convergence period because the repair node is guaranteed to have a path to the ultimate destination. So the PLR may not be able to use its best path to get to the destination, but if it can get traffic to the repair node can get it the rest of the way. Now, what are the differences between LFA, RLFA, and TILFA? Well, the biggest difference is how fussy they are about selecting a repair node. In LFA, the repair node must be directly connected to the PLR, and it must meet two other criteria that we'll talk about later. But the good thing is you don't need a tunnel to get to it, and it gives you pretty good coverage. In many network topologies, LFA is good enough to give you fast reroute. But in some network topologies, LFA will not give you fast reroute. That's why we say it's good coverage as opposed to 100% coverage. Now, RLFA has less severe restrictions on repair node selection. There are more nodes that can be the repair node. And the reason why is the repair node does not need to be directly connected to the PLR. If the PLR can reach the repair node over a tunnel that follows the pre-convergence IGP least cost path, that repair node is good enough. So the restriction on selecting a repair node is less severe. You do need a tunnel to get to it, and you get better coverage than LFA, but still you don't get TI-LFA. Then finally, we have topology-independent LFA. It has the least severe restrictions on repair node selection. In fact, you're guaranteed that there will be a repair node available. Again, you need a tunnel to get to it, and in particular, you need a segment routing tunnel. The difference between the tunnel you used in RLFA and the one you use in TI-LFA, the tunnel in RLFA follows the pre-convergence IGP least cost path. The tunnel that you use in TI-LFA can follow any path that you want. And it gives you the best coverage. It gives you 100% coverage, so there's guaranteed to be a repair node available. So let's take a little look. What we're going to do is take a look at all three fast reroute solutions, LFA, RLFA, and TI-LFA. We're going to take a look at a reference topology and take a look at, first, how a repair node is selected and how we use it. Then we're going to tweak the topology a little bit to show you a topology in which, in this case, LFA does not work. And we'll go on to RLFA. Do the same exercise, and we'll tweak the topology a little bit and show you a topology in which neither LFA nor RLFA will give you coverage. And then we'll go on to TI-LFA and show you how it gives you 100% coverage. So let's talk about LFA first. LFA preserves connectivity during the LFA preserves connectivity during convergence by pre-computing and installing a backup route to the destination. When the primary route becomes unusable, traffic shifts to the backup route. So let's go through an example. In the example topology, R2 calculates its least cost path to R7. And that least cost path traverses the link between R2 and R5. That's the link that's highlighted in yellow. It also identifies a repair node. And in this case, the repair node is R3. So let's say for a moment that R2 fails. If R2 can get traffic destined for R7 to R3, it has a guarantee that R3 has a path to R7. And things will just work. Now, what do we do before the break? Well, R2 calculates its least cost path to R5, to R7 through R5. It identifies a least cost path to the repair node through R2, R3, and it installs that path as a backup to R7. So we need a couple pieces of terminology here. First is PLR. In this example, R2 is the PLR. It is the node just upstream of the protected link, and it will detect the break on the protected link first. It also identifies the repair node, in this case, R3. Now, what are the requirements to be a repair node? Well, first and foremost, the repair node has to be directly connected to the PLR. Second, it has to satisfy the loop-free criteria. This means when R3 is in its pre-convergent state, before it notices that R2, R5 has gone down, its least cost path to R7 must not go back through R2. And as it turns out, that's exactly the situation here. R3's least cost path to R7 has a metric of 1, 2, 4, 6, whereas if it went back through R2, the metric would be 1, 5, 7, So R3's least cost path to R7 is not back through R2. You can see why you wouldn't want it to go back to R2. If R3 sent the packet back to R2, R2 would just send it back to R3, and you'd have a routing loop. The next criteria is the downstream criteria. That is, the IGP metric from the repair node to the ultimate destination has to be less than the IGP metric from the PLR to the ultimate destination. And that kind of makes sense. The repair node has to be closer to the destination than the PLR. So what happens after the break? R2 notices that link R2-R5 is broken. It sends traffic destined for R7 to R3. R3 forwards the packet the rest of the way to R7, and it gets there. Continuity is preserved during the break. And when the IGP reconverges, now R2's least cost path to R7 will also be through R3. Now, I'm going to tweak the IGP a little bit. In the last slide, the IGP metric of R3, R4 was 1. Now I'm going to tweak it up to 3. Well, now R3 is no longer a repair node for R2. And the reason why, the metric between R3 and R7 going through R4, R6, R8 is 3, 4, 5, 6, 7, 8. While the metric going back through R2 is 1, 5, 7. So if R2 tried to send a packet destined for R7 to R3, R3 would just send it right back to R2. You'd have a routing loop, and that would be worse than black holing. So what we're seeing is the basic limitation of just plain old LFA. In some network topologies, there is no repair node. So in this particular network topology, LFA cannot protect link R2, R5 with respect to destination R7. So this brings us to remote LFA. How do we get around this problem? Well, RLFA addresses LFA limitations by allowing some nodes to serve as repair nodes, even if they're not directly connected to the PLR. So what does that mean? In LFA, the only possible repair node was R3. Now, other nodes can serve as the repair node, but you need to build a tunnel from the PLR to the repair node. And that tunnel will follow the pre-convergence least cost path from the PLR to the repair node. So let's take a look at the exact same topology we had a couple slides back. This is the topology in which LFA would not work because the metric between R3 and R4 had been elevated to 3. So again, RLFA is protecting link R2, R5. That's the link highlighted in yellow. R2 calculates its least cost path to R7, and it's still through R2, R5, and it installs that as the primary. Now, R2 identifies a repair node. This time, R3 is not the repair node. R4 is. And you'll notice R4 isn't directly connected to R2. The PLR and the repair node aren't directly connected. So R2 has to create a tunnel to the repair node. And this tunnel follows the IGP least cost path from the PLR to the repair node. And then it installs that tunnel as the PLR, R2, installs that tunnel as a backup route to R7. Now, what are the requirements for a repair node? This part of the talk is going to sound a little scary because I'm going to start throwing P's and Q's around, but it's really not that complex. So try to hang with me. The repair node has to be in the PQ space. Now, what's the PQ space? The PQ space is the intersection of the PLR's P space and the destination's Q space. So we're going to define two things. The PLR is going to have a set of routers in the P space. The destination is going to have a set of routers in the Q space. And any node that is in both sets is in the PQ space. Now, what is in the PLR's P space? The PLR's P space contains nodes that it can reach in its preconvergent state without traversing the protected link. So, in this example, R2 in its preconvergent state can reach R3, R4, R6, and R8 along the pre-computed path, along the least cost path without traversing the protected link. You'll notice that it can't reach R5. R5 is not in R2's P space, and the reason why is R2's least cost path to R5 is through R2, R5, and that's the protected link. So it's just not there. Now, the next thing we have to understand is the destination's Q space. What's that? The destination's Q space contains the nodes that can reach the destination in their preconvergent state without traversing the protected link. And in that space, we have R5, R4, R5, R6, R7, and R8. You'll see that R3 isn't in that space. If the destination wanted to reach R3, it would go through the protected link. So now we're looking for nodes that are in both the P and the Q space. And the intersection is R4, R6, and R8. So R4, R6, and R8 are all candidates for being the repair node. And in this case, we pick R4 as the repair node. The reason why is it's closest to R2. Also, it's going to illustrate a nice little point in a minute. So what happens after the break? The link breaks and becomes unusable. R2 starts sending traffic destined for R7 through the backup route, that is to R4. R4 releases packets from the tunnel and sends it to R7. Now, let's take a look at R4's path to R7. You'll see that it has two equal cost multipaths. One goes through R6 and R8. The other goes through R6 and R5. And both are leveraged because this is just an IP packet and it's going to do the load balancing the way IP does. Now, let's talk about node protection for a while. The difference between link protection and node protection is what is protected. In the previous slide, you saw the link between R2 and R5 highlighted in yellow. That meant we were worried about it breaking. Now, R5 is highlighted in yellow. So what does that mean? When R2 detects link R2, R5 is down, it assumes that the reason for that outage is that R5 itself is down. And if R5 itself is down, all of the links connected to R5 are also down. So in the case of node protection, R2 not only wants to avoid link R2, R5, but it needs to avoid R5, R6, and R5, R7, all of the nodes connected to R5. So what does it do? Again, it calculates its least cost path through R2, R5. Then it identifies a repair node, but this time it can't identify R4, because if R4 were the repair node and the traffic were released at R4, R6 would send it across the equal cost multipath and you'd traverse R5. So in this case, there is only one candidate to be the repair node. That's R8. So instead of building a tunnel from R2 to R4, this time we build a tunnel from R1 to R8. When the link breaks, packets go along that tunnel. R8, the repair node, releases packets from the tunnel, and R8 forwards it along the one and only path to R7, and that's through R8, R7. Now, in node protection, what are the requirements to be a repair node? The repair node has to be in PQ space. That is, it still has to be in the intersection of the PLR's P space and the destination's Q space. Here's the difference. The PLR's P space contains nodes that it can reach in its preconvergent state without traversing the protected node. So here the p-space is R3, R4, R6, and R8. The destination's q-space contains nodes that it can reach the destination in their pre-convergent state without traversing the protected node. And here only 7 or 8 are in the q-space, and this is because of that ECMP. So here only R8 is a candidate for the PQ space. So we're starting to feel pretty secure now. We think that we have things well in hand. You know, using tunnels, you expand the number of candidates you have as repair nodes, and you get better coverage, but you don't get 100% coverage. Here, I've tweaked the IGP metric on this link one more time. First time you saw the metric, it was set to 1. Second time you saw it, it was set to 3. This time it's set to 7. In this example, again, R2 protects, LFA protects the link R2, R5, and the IGP metric associated with R4, R6 has been cranked up to 7. Now, R2's p-space only contains only node R3. Because the IGP metric from R3 to R4 is so high, that path through R3 basically is the least cost path to nowheres. The least cost path to almost every place is through the broken link, R2, R5. So the p-space has only R3 in it. The q-space still contains R2, R4, and R5, and the PQ space is empty. So in this topology, R2 can't find a repair node for R7, and you just can't get 100% 100% coverage in this topology. Now, really the problem is in RLFA, the repair tunnel, the tunnel that connects the PLR to the repair node, follows the pre-convergence IGP least cost path. Wouldn't it be nice if you could have a repair tunnel that's traffic engineered? It follows any path you like. So now the p-space gets very large. In fact, the p-space would include every node in the domain. And this is exactly what you get with TI-LFA, topology independent loop-free alternates. Okay, we already talked about RLFA limitations, the fact that you can't get a repair node for all, you can't get a repair node for all topologies. So let's talk about how TI-LFA works. In this application, TI-LFA is protecting R2, R5, again, the same link. Again, R2 calculates the least cost path to R7, and it's going through R2, R5. So it installs that as its primary link. Now, it identifies a repair tunnel. And in this case, it can pick R4 as the repair tunnel, because so long as R2 can get the packet past R3 into R4, R4 can release the packet from the tunnel, and it will get the rest of the way to R7. Notice that this repair tunnel doesn't follow the least cost path from R2 to R4. The least cost path from R2 to R4 is through R5 and R6 across the broken link. So this is a traffic engineered repair tunnel. The way this repair tunnel works is R2 pushes an SR MPLS label onto a stack and forwards the packet to R3. R3 pops that label off, and that label is an instruction. The instruction says, forward this packet along the link R3, R4. Send it to R4, whether or not that is the least cost path to R4. And that solves your problem. Now you can deliver the packet to R4, which is a perfectly good repair node, even though R3 is not on the least cost path from R2 to R4. Now, R2 installs this tunnel as a backup route, and you'll see that it gets used when the link breaks. Now, what are the requirements for a repair node when we're doing TI-LFA link protection? Well, the repair node has to reside in the destination node's queue space. That's to say, the destination node can reach it in its pre-convergent state without traversing the protected link. So nodes 4, 5, 6, 7, and 8 are all in 7's queue space. Notice there's no real requirement about P space because this is a traffic engineered tunnel, R2 can reach every single node on this router in this topology without traversing R2, R5. Now in this case, we choose R4 because it's the closest to the PLR. So what happens after the link? After the link breaks, R2 realizes the link's broken, so it starts sending packets along the backup path. It pushes label 1010, forwards the packet to R3, R3 pops the label, forwards the packet to R4, R4 sends it the rest of the way along the path. And again, R6 leverages that ECMP between between R6 and R7. So there's one path through R5, another through R8, and R6 will use both. Now, let's talk about node protection. We also have node protection in TI-LFA and TI-LFA. Here, the link isn't protected. It's node R5 that's protected. So when R2 realizes that the link to R5 is broken, it assumes that the reason for this is that R5 is broken, and all of the links that R5 connects to are also broken. So now you do not want R6 to be exercising that ECMP to R7. You don't want it sending traffic to R5. So your choice of repair tunnels changes. You don't want to use R4 as a repair tunnel because it would send traffic to R6 that would leverage the ECMP. You don't want to use R6 as a repair tunnel because it would leverage the ECMP. You want to use R8 as the repair tunnel. So what does this repair tunnel look like? Well, R2 creates a repair tunnel to the repair node. The repair tunnel has an outgoing PLR interface, that's the interface to R3, and it has a list of adjacency segments. MPLS, it has a repair list. And the adjacency segment 1010 that begins on R3 and ends on R4. So what happens in this? R2 pushes the label 2010 and then the label 1010 and forwards the packet to R3. R3 pops the label 1010 and that label causes it to forward the packet to R4. R4 forwards the packet all the way to R6, and it does this because of label 2020. R8 receives the packet, pops label 2020, and forwards the packet the rest of the way. So what you see here is this repair tunnel, the green line, it didn't follow the IGP least cost path from R2 to R4. But it was traffic engineered in such a way that it pushed past the nodes that it would have otherwise had to go through. In node protection, what are the requirements for the repair node? The repair node must reside in the destination's queue space, same as before, and that means the destination has to be able to reach the repair node in its pre-convergent state without traversing the protected link. So R7 and R8 are in the queue space. R4 and R6 aren't in the queue space because of the ECMP to R7. And in this case, we chose R8 as the repair node because it's closest to the PLR. We could have actually chosen R7 itself as the repair node. And here's an example of what happens after the break. This is exactly what I talked about a couple slides back. R2 pushes 2 labels on the packet and sends it through the repair tunnel to R8. So, wrapping up with some conclusions, TI-LFA is a fairly simple mechanism that can protect all nodes and links in all network topologies. And for this reason, we say that TI-LFA provides 100% coverage. TI-LFA is powerful enough to motivate network operators to deploy SR. There are many network operators who want their traffic to traverse the least cost path from source to destination. They don't want to do any traffic engineering at all, but they do want FRR. And FRR gives them 100% coverage in any network topology. So they deploy segment routing, not because they want to traffic engineer their normal traffic, but because they want to traffic engineer their repair paths. Well, that's it, and I'll open to questions now.
Thank you very much, Ron. We have 3 questions for you so far. If anybody else wants to get a question real quick, please submit it now, and I'll get into it if we have time. So the first question is, while doing segment routing traffic engineering, if the explicit node is failed, does TI-LFA have a mechanism to protect the node failure?
Okay, so first let's make sure I understand the question. The protected node is the endpoint of a prefix SID or of a node SID. The protected node appears to be down. I think the answer is that the behavior is configurable. One possible behavior is you drop the packet because you cannot get to the protected node. You're assuming the protected node is down. Another is that you just go to the next node. I'm going to have to check on that and see if our implementation actually does both, but I believe the behavior should be configurable.
All right, the next question is, for the LFA flavors, each node has to compute LFA for every other node in the network, yes? Does not that computation load get very large?
Yes, it is computationally expensive, and to reduce the expense, there are some optimizations. You might pick a repair node that is suboptimal, but good enough to reduce the amount of optimization. There are other things that you can do. Even in a fairly complicated network, we found that we can do good enough computations pretty quickly.
All right, and next question is, what is your opinion about the future of protecting SRTE policies by TI-LFA on transit nodes?
Okay, protecting TI-LFA policies on transit nodes. Let's see, and we are talking about in SR-MPLS?
It says SRTE policies by TI-LFA.
Okay, in that case, we're probably talking about SR-MPLS. And yes, it can be done on a transit node. Let's say, well, first of all, TI-LFA is all about prefix and node segments. Let's say you're in the middle of a node segment and you realize a link is down and you need a way to get to the segment endpoint. It's exactly as it was described in the slides. What you do is push a few more labels that get you to the repair node. And once, the repair node might be the segment endpoint, it might be a node on the path to the segment endpoint. But in either event, you're going to get there. The repair path, the labels that represent the repair path will go away, and you'll continue routing the packet on its merry way to the segment endpoint.
All right, thank you very much. I do apologize to all the questioners that we have run out of time, but I'm sure Ron would be perfectly happy to talk with you on the NANOG list or by some other mechanism.
Please feel free to email.
Yeah, that's it. Again, thank you very much. And that concludes our current session. Our next talk is the 5G Quick Start talk. Thanks.